These are the notes for AP Calculus on the topic of derivatives of trig functions. So we've got the derivative of sine is cosine, the derivative of cosine is negative sine. And then the other formulas for the derivatives of trig functions, derivative of tangent is secant squared, which we'll oftentimes write this way instead. Secant of x in parentheses squared, because that's what it really means. And the derivative of cotangent is negative cosecant squared, which we'll often write with a negative on the outside of the parentheses, so it stays negative. And then cosecant x squared. The derivative of secant x is secant x times tangent x. The derivative of cosecant x is negative cosecant x cotangent x. So, to help you memorize these, let's see if we can find some patterns to make it easier to remember them. Notice across here, the derivative of tangent is secant squared, and the derivative of cotangent is cosecant squared in the negative. The derivative of secant x is secant x tangent x. The derivative of cosecant x is cosecant x cotangent x in the negative. You see the similarity across the rows there. And also notice an easy way to remember the derivatives that are negative, right here, all the ones that start with a cosine, cotangent, cosecant, their derivatives are all negative. The ones that don't start with cosine, tangent, and secant, their derivatives are not negative. So the first couple examples are just proving that a couple of these formulas actually work. So it says prove the following using sine, cosine, and the quotient rule. So let's first, this says the derivative of tangent is secant squared. Let's prove that. So let's first rewrite tangent. Tangent is the same as sine x divided by cosine x. And now we can use the quotient rule on that. The quotient rule says we take the derivative of the numerator, the derivative of sine is cosine x, and then times the denominator as it is, which is cosine x, and then minus the numerator as it is, sine of x, times the derivative of the denominator, derivative of cosine is negative sine. And then all divided by the denominator as it is squared. So cosine x squared. And let's go ahead and simplify this. So cosine x times cosine x would give you cosine of x squared. And the negative we can pull out in front to make it a plus. Sine x times sine x is sine of x squared. All divided by cosine x squared. And remember, if you take a look at the numerator now, cosine squared plus sine squared, that's one of those trig identities that just equals 1. So this is the same as 1 over cosine squared. And 1 over cosine is the same as secant. And this is 1 over cosine squared, so that would be the same as secant squared. So that proves that the derivative of tangent actually is secant squared. But, so if you did forget this one, you could derive it this way. But to be more efficient, we want to have it memorize the derivative of tangent secant squared, so we don't have to go through this process every single time we need the derivative of tangent. All right, let's take a look at proving that derivative of secant is secant x tangent x. So again, let's first rewrite secant x using sine or cosine. Secant, remember, is 1 over cosine. Alright, so again, let's use the quotient rule on that, which says we take the derivative of the numerator. Derivative of 1 is 0 times the denominator as it is, cosine x, minus the numerator as it is, which is just 1, times the derivative of the denominator, derivative of cosine is negative sine. All divided by the denominator as it is, cosine x. Well, 0 times cosine wipes that out, that's 0, and then the negatives cancel, so we're left with sine of x over cosine of x squared. So how's that going to be? That's our derivative, but how's that the same as secant x tangent x? Well, if we split up the fraction, we split the cosine up into 1 over cosine x times sine over cosine x. See, that's the same as what we have. We just split into two fractions. And 1 over cosine, you can see that's the same as secant x. And sine over cosine is the same as tangent x. That proves the derivative of secant is secant x times tangent x. Again, though, it's easier to memorize it than having to go through this process every single time you need a derivative of secant. All right, let's see how we use these new formulas in conjunction with the power rule, product rule, quotient rule, and chain rule. All right, so in this one it says find the derivative of each expression. So we've got x cubed times tangent of 4x. Notice we've got 4x inside of tangent. But big picture, we've got x cubed times that. So overall, we're going to have to use the product rule. So take the derivative. So f prime of x. Start out with the derivative of x cubed is 3x squared. So the derivative of the first one, 3x squared, times the second one as it is, tangent of 4x. And the product rule then is plus the first one as it is, x cubed, times the derivative of the second one, and that's where we're going to need the chain rule as well. So normally the derivative of tangent, remember, is secant x d secant x squared, but here it's tangent not of x, but tangent of 4x. So the derivative of tangent of 4x, we would start with the derivative of the outside using chain rule, is secant, the function inside stays the same, of 4x squared. And then the chain rule says we also have to multiply that by the derivative of the function inside. The derivative of 4x is 4. There's not much to simplify here. So we've got 3x squared, tangent of 4x, then bring the 4 out in front. So plus 4 times the secant of 4x. Now let's take a look at the next one. We've got g of x equals cotangent x divided by x. So the derivative would be g prime of x. And here we can see we need the quotient rule. Now you could move the x up to the numerator and make it x to the negative one and use the product rule instead, but that's going to do a lot more negative exponents. It's going to be more difficult to simplify. So that's why we have the quotient rule. The only time it's usually useful to move that up the numerator is if the numerator is just a constant, which it's not. It's cotangent x. So let's use the quotient rule instead on this. So quotient rule says we take the derivative of the numerator, derivative of cotangent x. Remember, it starts with a co, so it's negative, and derivative of cotangent is negative cosecant x squared times the denominator as it is, which is just x, and then minus the numerator as it is, cotangent x, times the derivative of the denominator, derivative of x, which is 1. All divided by the denominator as it is squared. And really there's not much to simplify in this one either. Just bring that x out in front along with the negative. Usually the trig functions are at the end of each term. So negative x cosecant x squared, and then minus cotangent x, and 1 is just cotangent x, all divided by x squared. Now let's look at finding the derivative of this one. Well, let's first rewrite this. See what's being raised to the fifth, that's cosecant x raised. So we can write 2. Now we've got cosecant 3x, cosecant 3x is raised to the fifth. So this one we've got two functions inside. We've got the cosecant inside the fifth power and the 3x inside cosecant. So this is our double chain rule. So we start on the outside and work your way in. Since we've got y equals, the derivative would be written as dy dx. Start on the outside, that'd be bring down the 5 times 2 is 10. Cosecant of 3x to the fourth, using the power rule, reduces x by 1. And then we take the derivative of the next function inside, which is cosecant of 3x. Normally the derivative of cosecant x is negative cosecant x cotangent x, but here it's cosecant 3x. So when we multiply the derivative is negative cosecant 3x times cotangent 3x. And then we have to multiply, so there's two functions inside, by the derivative of 3x, which is 3. And then to simplify, we can pull the constant 3, the negative, and the 10 out front to use negative 30. And we get cosecant of 3x to the fourth times, actually, up to the fourth. We've got times another cosecant of 3x, so actually it's to the fifth. And then times cotangent of 3x. Now let's take a look at one where we've got three terms here, pluses and minuses. So we take the derivative of f prime of t. Notice on the first one we've got negative 5t times the secant of 2t. So there we're going to need the product rule. And we've got a 2t inside of secant, so we'll also need the chain rule there as well. So let's take the derivative of the first one, which is negative 5. Negative 5t times the second one as it is, secant of 2t. And then normally it's plus on the product rule, but it's plus the first one as it is, which is negative 5t. So it's already negative in there. So you don't see that plus sign. And then we take the derivative of secant of 2t, using the chain rule. Start with the derivative of secant. Normally the derivative of secant x is secant x tangent x, but here's the secant of 2t. So that's secant of 2t times the tangent of 2t. The function inside 2t stays the same. But using the chain rule, that requires us to take the derivative of the inside and multiply by that. Derivative of 2t is 2. And then on the second term, let's go ahead and rewrite this one. This is the same as 2 tangent of t cubed. So it's easier to see the function inside. We're going to need to use the chain rule, and on the outside the power rule. So using the power rule on the outside, remember these pluses and minuses here mean we can take the derivative of each of these separately. So we already took the derivative of the first term. Now we're taking the derivative of the second term. So using the power on the outside, we plus 6 tangent of t squared times the derivative of tangent of t is secant of t squared. Using the channel, and then the derivative of negative 3 by itself is just 0. So there's not much to really simplify here. Negative 5. Secant of 2t, we bring those 2 out in front times the negative 5t using negative 10t. Secant of 2t, tangent of 2t, and then plus 6 tangent of t squared times the secant of t squared. Let's take a look at one where we're trying to find the equation of the tangent line and then the normal line. So remember the two things we need to write the tangent line are the point of tangency and the slope. So let's go ahead and find the point of tangency first. There's our x-coordinate, so we just substitute that in to find the y-coordinate. So to be cosecant, well, we multiply pi over 8 times 2, that becomes pi over 4, plus, same thing here on the cotangent, 2 times pi over 8 reduces to be pi over 4. So we have to value visit pi over 4. Let's go ahead and draw that. Already get the circle here. We can see pi over 4. It's a 45-degree angle. And the sides are 1, 1, and square root of 2. So cosecant is the reciprocal of sine. So sine, remember, using SOHCAHTOA is the opposite over hypotenuse. So the cosecant would be hypotenuse root 2 over 1. And then plus, cotangent is reciprocal of tangent. Tangent is the opposite over the adjacent. So cotangent would be adjacent over the opposite, which is 1 over 1 also. So that gives us square root of 2 plus 1. There's your y-coordinate. So your point of tangency is pi over 8 and square root of 2 plus 1. Now that we have the point of tangency, we just need to get the slope, and that comes from the derivative. It gives you the slope of the tangent line. So, notice we got 2x inside both of these, so on both of them it's going to require the chain. But they're added, so we can take the derivative of each one separately. So f prime of x cosecant on the outside. It starts with a cos, so negative cosecant 2x times the cotangent of 2x. Using the chain rule, says we have to multiply by the derivative inside. Derivative of 2x is 2. And normally it would be plus, but it's plus. Derivative cotangent is negative cosecant. In this case, 2x. The function inside stays the same, squared, times the derivative of 2x equals 2. And now we want to just plug in pi over 8. So f prime of pi over 8 be negative, well, pi over 8 times 2 is cosecant, becomes pi over 4. Same thing here, 2 times pi over 8 is pi over 4, so cotangent pi over 4. I'll bring the 2 out in front there. And then minus 2 times cosecant, again, 2 times pi over 8 is pi over 4. So we already evaluated these over there, so we've got negative 2 times cosecant of pi over 4. Remember, was root 2 over 1. That's just square root 2 times the cotangent of pi over 4, which is 1 over 1, so 1. Minus 2 times the cosecant of pi over 4. Again, was square root 2 times the square. So f prime of pi over 8 is negative 2 root 2 minus square root of 2 squared is 2 times negative 2 gives you negative 1. So that's the slope of the tangent. So let's go ahead and write down our tangent line and normal line. Tangent line would be y minus the y coordinate. But notice there's two terms, so make sure you put in parentheses. It's square root of 2 plus 1. Or you can distribute out the negative if you want to get rid of the parentheses. Equals the slope. Also has two terms, so put in parentheses. Negative 2 root 2 minus 4 times x minus the x coordinate, which is pi over 8. And then the normal line, remember, also goes to the point of tangency, so the same point, but it's perpendicular to the tangent line. So perpendicular lines, remember, have slopes that are opposite reciprocals. So it'd still be y minus square root of 2 plus 1 in parentheses equals. But then here we'd have to do the opposite reciprocal of that. So let's first do the reciprocal. Do 1 over this, and then to make it the opposite, you can either put the negative on the 1 here, but since these are both negative, it's probably easiest to just multiply those both by negative 1 to make them both positive. So now it's the opposite reciprocal, and then times x minus pi over 8. So there's our tangent and normal line, and that concludes the notes for AP Calculus on the topic of derivatives of trig functions.